Hi everyone, welcome to our video on acids, bases, and the pH scale. Now, even though the electrons within water molecules are unevenly shared, they usually remain covalently bonded. But in some cases, the hydrogen can lose its electron altogether, resulting in the formation of a hydroxide, OH-, and a hydronium, H3+ ion, which we normally just refer to as H+. While it doesn't happen extensively, this does happen in water and has an important influence on biological processes. The pH scale ranks substances based on their hydrogen ion concentration. Acids, like coffee, wine, or lemon juice, for example, are substances that increase the hydrogen ion concentration of the solution. Bases or alkalis, like baking soda or oven cleaner, for example, are substances that decrease the hydrogen ion concentration. In either case, we're always describing the hydrogen ion concentration of the solution rather than the hydroxide ion concentration. As we just mentioned, pH describes the hydrogen ion concentration of a solution, and it's actually defined as the negative log of the hydrogen ion concentration. We know that in aqueous or water-based solutions, at 25 degrees Celsius, which is generally considered to be around room temperature, the product of the hydrogen and hydroxide ion concentrations is always 10 to the negative 14. And this makes calculating pH relatively simple, as long as you can count to 14. In a neutral solution, the concentration of hydrogen ions and hydroxide ions is equal. And since the product is 10 to the negative 14, that means that the hydrogen ion concentration must be 10 to the negative 7. This means that the pH is the negative log of 10 to the negative 7, which is negative 7, which is 7. So, once you have the hydrogen ion concentration, whatever the negative exponent is, that's your pH. If it's 10 to the negative 12, for example, then your pH is 12. If it's 10 to the negative 5, the pH is 5, and so on. Now, if you have that, you can get to the hydroxide ion concentration too. If your pH is 5, then the hydrogen ion concentration is 10 to the negative 5. So the hydroxide, OH- ion concentration is negative 14 minus negative 5, which is negative 9. So as long as you can count to 14, and you have either the concentration of one ion or the pH, you can find all the others. Just remember that the exponent will always be negative because we're dealing with really small concentrations, and the pH will always be a positive number between 0 and 14. Also, bear in mind that because we're dealing with a logarithmic scale, each step is a tenfold change. So to go from pH 7 to pH 6, the hydrogen ion concentration goes up tenfold. To go from pH 7 to pH 5, we'd have a 100-fold increase because it's 10 times 10 for the two steps. It's important that biological systems maintain a relatively constant pH, as pH changes can affect the structure and function of various molecules. Now, this doesn't mean that all biological systems require a neutral pH. While many do, there are examples like the stomach that requires the pH to be closer to 2, which is a strong acid, while the intestines function at around pH 8, which is slightly alkaline. The exact pH that is required depends on the system and the function, but it's important to keep the pH close to its optimum for that specific situation. To accomplish this, many biological components act as buffers, substances that can add or remove hydrogen ions from a solution depending on the conditions. These are typically substances that ionize to form a hydrogen ion and a basic ion. The example shown here is the carbonic acid bicarbonate system that buffers the pH in the bloodstream. If the pH increases, that means the concentration of hydrogen ions has gone down. And so, the carbonic acid, H2CO3, will ionize to release extra hydrogen ions into the solution. If, on the other hand, the pH decreases, the bicarbonate HCO3- ion will absorb some of the extra hydrogen ions, converting back into carbonic acid. Thanks for watching. Please make sure you check out the other videos on the various properties of water.